I think we will discuss about the module. So we have the advanced signal processing module today. So we'll be learning about signal processing, and we will learn about how we can mathematically model the signals that we have in our environment. So what exactly is signal processing? So what exactly is signal processing? Signal processing involves transformation of signals into a useful format, right? So signal processing involves the transformation of signals to enhance the characteristics uh, of its signal, of the signal, involves the transformation of the signals to enhance its characteristics. So signal processing is transforming a certain signal to enhance its characteristics. So for example, we'll be looking at noise cancellation, uh, filtering, and so on. So by doing those, we are hoping to increase the quality of the signal that we have and increase its usefulness. And by doing that, we are trying to take information from those signals. So basically, in signal processing, we'll be looking at signals, and we will be looking at how to process them to obtain information from them. So there are many, applications of signal processing. As you saw just before in the video, there are many applications in different domains. So one such domain is communications, communications engineering, and in communications. So in this communications, we consider like wireless communication, wired communication. So when we take wireless communication, we have signal processing. When we have wired communication, we have signal processing. So in those situations, we are dealing with signals, and we are dealing with noise interference, and we need to remove the noise interference and take the information out of the signals. So when we take a phone call, we connect with a certain base station, and the base station will receive our signal that we send to the base station as an electromagnetic wave, and then that signal needs to be processed at the core network that receives the signal, and the core network has to do maybe some kind of a processing, and then it needs to forward it to the destination. So that is one application that we can consider signal processing. Then we also have signal processing in entertainment area. So currently, when we take entertainment, we are talking about, image processing, video processing, image processing, video processing, and much more. We have new concepts that are adding to this entertainment sector. So wherever we have signals, we need to process those signals. We also have applications in healthcare where we have to obtain signals such as ECG and MRI, and then using those signals, we need to make some conclusions about the data. We need to obtain information from the received signals. So apart from that, some other applications can be in like various other domains as well. We will talk about them in a later instance as well. And then we will now consider a small example, right, to explain a little bit about how we use, signal processing. So, when we have devices, uh, uh, when we use some device, it has many sensors in it. We have many sensors in devices. So, if you take, for example, the smartphone, the smartphone has many sensors in it. So these sensors obtain information and provide that collected data as a signal. So the sensors, they provide signals. The sensors collect the data and provide signals, and those signals need to be processed. So it will go through the processing stage. So what do we mean by this processing exactly? So as I said before, we are trying to understand, or we are trying to extract the useful information from the signals, right? So in order to extract the useful information from the signal, we need to analyze the signal in different domains. So we will analyze uh, the signal in time domain, in frequency domain mainly. After that, we are going to go for inference and estimation. Inference and estimation, where we are going to estimate the information or the signal that we received to a certain output. We are going to estimate the received signal, and we are going to give a measurement to the to that parameter. So anyway, we are going to estimate the signal that we got, and we are using that estimate to obtain information about the signal. Apart from that, after making the estimate, we can do high-level analysis of the we can do high-level analysis using the estimates. High-level analysis using the estimates. So high-level analysis means we are going to do analysis such as behavioral analysis, behavior analysis, and disease detection. So high-level analysis means basically the situation of the case. I mean, high-level analysis means the case of applying the estimation that we made for a certain specific application, such as behavior analysis, disease detection, like predictive maintenance likewise, right? So basically, after we find a way to estimate our signals to a certain useful information, then we use that information to apply that to for a certain application. So using the information that we using the information that we derived in the previous stage, we can use that information to detect a certain disease, to detect a certain behavior, or to predict a certain process in a certain environment. So yeah, if you have any questions, you can let me know. In here, I'm mentioning inference and inference and estimation. The before high level analysis, we are going to do inference and estimation process. So in there, we are going to estimate our I mean our signal. We are going to use estimation methods. We have specific estimation methods, for example, maximum likelihood estimation, MLE, and least squares estimation, LSE. So we are going to use some algorithms to um, do some estimations on the received signals. Sorry, not interference, inference. Inference. Inference and estimation. Uh, so this is the overall process of signal processing and how we are using it for an actual application. So nowadays we have large number of devices that depend on sophisticated signal processing algorithms. So there are a large number of products that depend on signal processing algorithms. So the I mean the reason being the development of electronics and the development of multiple sensors to obtain data about different environments. So currently we have multiple sensors, numerous sensors to obtain data regarding different parameters in the environment. So once we have different parameters in the environment and once we have sensors to collect them, the sensors will collect that data and will form a signal and provide that signal to the signal processing unit. So once we have that signal in that signal processing unit, then the processing will be happening in that processing. So there are large number of devices that are used in signal processing, such as like hearing aids, microphones, medical imaging. We have also radar systems. So it is known that radar systems is one of the earliest applications of signal processing, mainly being a system which basically transmits and receives signals from a distance location. And that system is a very simple system. So I don't know whether you have visited a place like maybe you have seen if you go to the any kind of transmitting place with a radar system. You can observe the radar system using signals to identify objects in in a distant place. So we basically have like a uh, like a metal object that can detect signals that are coming from a distant location, and that signal is uh, sent to this processing unit, which is obtaining that signal, and that unit will process the data and uh, identify at what location this object is. So it will like find in the screen at what location a certain object is around that area. So anyway, like radar systems has been one of the most earliest forms of, I mean, products that used signal processing, and that led to other inventions afterwards. So radar system is one of the applications, and there are many applications in communications that are related to signal processing. Uh, okay, so I think you're asking about, I'm actually writing the note in this board. So I was writing about sensors and how the sensors will obtain the signals and process them and make the estimation and then make the analysis of the signals. So I will, if you want, I will draw that diagram again, right? So after explaining this section, okay? So I will explain what I did before again. So anyway, I will continue here, right? So smartphones is another application with signal processing. Another application will be vehicles, autonomous vehicles, autonomous drones, UAVs, autonomous vehicles, drones. Drone is drone is a flying vehicle, so it is somewhat different to the normal vehicle. So that is why I'm mentioning it separately. So autonomous drones, we also call it in the scientific world as UAVs. UAVs, or it is known as like unmanned aerial vehicle. Aerial vehicle. So in those I mean applications, we use signal processing in a in multiple ways. So something that we can see in all these applications is that all these applications are embedded with sensors, right? All these applications have sensor modalities in them. So they have sensor modalities in them. They have sensors embedded in them. We call that sensor modalities in them. They have sensors, embedded sensors. So once they have those sensors, the data that the sensors collect are processed afterwards as signals. So that is after the sensors send the signals, the signal processing part begins. So that is where the signal processing comes. So uh, anywhere that we can find devices with the sensors, we can say that we have signal processing. So So I will draw the previous diagram again. I think it is better. So as I said, whenever there's some sensor, we have that sensor will provide some signal, right? The sensor will provide some signal, and that signal will then be processed using some processing techniques. Okay, so we will use some processing techniques, and we will basically analyze that signal that we receive in the time domain or in the frequency domain. After analyzing, we can make some estimates regarding the data that we have received. So in that stage, we are calling that inference and estimation. I'm sorry, my writing is like this. So inference and estimation, okay? Inference and estimation, in that stage, we are estimating the data we have to a certain output. We are estimating the data to a certain output. And then using the output, we are going to do some predictions or some kind of detection. So using the estimations, we are going to do some high-level analysis of the environment. High-level analysis of the environment that we are considering. So those high-level analysis can be, for example, some kind of a behavior detection. Right? So using the estimate, we can detect whether there's some behavior or some kind of a person walking in the environment that we can conclude. We can also detect disease detection. Disease detection. Then we can have other predictive maintenance. We can predict about some kind of a process. Predictive maintenance. So, is it okay?
Okay, madam. Thank you very much.
Great. And so in this, I mean, MSc program, we are talking about signal. I think our main title is electronics and communications. So since there's communications part in that MSc, in our MSc program, so what is the communication? What is the relationship between signal processing and communication? What is signal processing and communications? So that is the question. So why do we need communications part in here, right? So basically, like signal processing enables us to obtain information from signals, right? Signal processing enable us to obtain useful information, and communications basically enable us to transfer that information from one location to another location. right? So signal processing basically helps us to extract useful information about about the data we collect. So useful information from signals, then communications help us to transfer that data over long distances, transfer that useful information over long distances. So I hope that it is clear to you why it is useful to have communications aspect in this in this domain, in the signal processing domain. So in this world where we want to obtain information regarding points on Earth which are distant from us, we therefore use communication technologies to get the data from those locations. So another question is, what is the role of sensors? What is the role of sensors in the signal processing? Uh, sensors help us to collect data. So it is hard to collect information without uh, a certain sensor-based electronic circuit. And then um, we also have some kind of uh, signal processing done at the sensor level itself. So the sensors allow us to do some signal pre-processing, signal pre-processing. So the at the sensor level, we are doing some signal pre-processing. That means we are uh, we are doing some noise filtering. I mean, filtering of noise. Um,
Madam, we can't hear you. Mic is muted.
Sorry. I'm
We could
sorry.
give
I
you
thought it
anything
was.
before like 2 or 3 minutes of time.
Sorry. Actually, I think I got a phone call, and then I think during that time I was muted automatically. Sorry about that. So
That is
I will
during
explain. Sorry.
signal pre-processing when you start that one. Onwards the
Uh,
mic will muted.
okay. Sorry. Then I will explain that, and then the one of the methods of doing pre-processing is noise cancellation and filtering, and the second one is bias compensation. So the bias compensation means that whenever there's some kind of a sensor, that sensor has a in like some I mean most of the sensors have inbuilt bias in the measurements that they make. So when that sensor makes some measurement, uh, uh, it it uh, it adds this error to all the measurements that it makes. So if it measures a certain distance from from its location, from the sensor location, if it measures the distance to of a certain object, right? There's some object here, and then that distance measurement will the actual distance measurement, I mean actual distance will be, let's say, this distance, but the sensor is measuring this distance as the distance to the object, right? So this difference that is happening here will be known as the bias. So if we take that difference as alpha, then there's an alpha bias of the sensor. uh, then whenever we make the distance measurement, then we need to either add or subtract this alpha bias from the measurement, right? And that addition and multiplication, sorry, addition or subtraction and compensating the error is known as the bias compensation. I hope it
So
is clear.
yeah, is it like error correction?
Yeah, it is error correction.
Okay, thank you.
So likewise, sensors are able to sensors. So with regard to sensors, we will have to consider. We have to consider the bias, and then we have to do the bias compensation. Then when we take the other application, other application of the sensors in signal processing, it's one of the other applications is feature extraction. So in the feature extraction, we can enable the sensor to extract specific. We can enable the sensor to extract specific attributes of the data. right? So likewise, there are many, places where we do signal processing related activities. I mean, in the sensor node level. So we can do some, those kind of processing at the sensor node level itself, and then we can then send that signal over to another location. So I think now I will discuss about another example where we use signal processing and um, communications. So we can take an example where we have both signal processing and communications. And I will take an example where we have, let's say, a drum playing, and then that drum, that whatever the music that is produced by that, uh, the the drum will be recorded using a microphone. We can record this using a microphone. And in this situation, we will be using signal processing related techniques such as analog to digital conversion, or ADC, analog to digital conversion. And in there, we will be using sample theory concept. So we will be using sample theory concept when we convert the analog signal to a digital signal. And then this mic will send the signal it received to a certain unit, right? So where we will be processing the signal further. So before processing here, at the mic, we will be having a digital signal, and because we are converting the analog signal to a digital signal uh, at the mic, and we will be able to have a digital signal output from the mic. So the digital signal will flow from the mic to the processing unit, music uh, processing unit. So during this location, we will be doing some processing, and we will be removing unnecessary data, removing noise, likewise, and we will process the signal. So whatever the signal we have received from the mic will be processed here. That signal that we have processed will then be transmitted to a certain server using Ethernet cables, for example, Ethernet cable. And then we will have a certain server which receives this information. So this information will be received as a certain packet, and the data packet will be received at the server. And that data packet will then be transferred across multiple routers and switches to the internet. So afterwards that data will be transferred to like telecommunication service provider. So, and let's say the core network of the telecommunication service, and the core network will forward that to um, either base stations, or via fiber cables to the optical fiber network. Then the optical fiber network will distribute that data to homes, right? So the homes or the residential places will receive the data, and that data will be received and demodulated using like a modem, right? We can use a modem to demodulate the signal received, and that signal that we receive will be connected to basically will be connected to Wi-Fi router, and the Wi-Fi router will have some antennas in it, right? The Wi-Fi router will have some antennas, and that antennas will propagate the data using wireless communication, using wireless media to the end device, which is receiving that data. So this end device could be like a smartphone, and that smartphone will receive the data from this router, for example. And so the smartphone will read the signal again using signal processing techniques. It will filter the signal, it will sample the signal, it will it will reduce the noise. We'll do some noise cancellations, right? We'll do some noise cancellation, and then by doing all that, it will receive a certain quality signal at the end device, at the smartphone level. So that is an example that we can use to identify the applications of signal processing in a real world scenario. So all these signals that we uh, observed in this situation are basically, having some randomness in it, right? So in order for us to get some useful data from the signal that we receive, for example, from this drum, let's say, like from this drum, we are receiving some signal, right? So that signal contains some information. In order for us to get the useful information, we need to mathematically model this random signal. Okay, so therefore we have to use mathematics to model the signal processing techniques, and we have to mathematically model the signals that we receive, and then we need to understand what are the components in that signal and so on. So we will get into that next. Right. So in the real world signals, contain uncertainty and randomness. Okay, so, right? So the signals that we receive from the sensors will have some randomness in it. So once so in order for us to get some useful information, we need to understand how this random signal works. What is the pattern, or what is the uh, what is the like what is something that they do repeatedly. So in order for us to understand the random signals, we have to mathematically model the random signals. We need to mathematically model the random signals to to understand their behavior, right? We have to mathematically model the random signals right? The random signals that we observe in the real world to obtain, to I mean, to study them, and to study their behavior, and study their behavior and um, obtain obtain information. And one thing is obtain information, and then we can also predict their behavior in the future. So predict behavior in the future. So I think you have heard about machine learning. So machine learning is a technique where we can use data to predict some kind of output. Where we can use data to predict some kind of output, right? So this generation of data that we need to do the prediction can come from signal processing, right? So from signal processing, we can obtain the useful data uh, from which we are doing the prediction, right? So therefore, like most of the time before doing this machine learning, we normally do the signal processing that is required, right? We do the signal processing first, and then only we can decide about what is the best machine learning technique to use in that application, right? So therefore, we need to first finalize the data in a useful format. So I'm going to erase this. Right. So in order to obtain the data, in order to mathematically model the data, we will use different mathematical concepts. Okay. So signal processing is basically based on a lot of mathematical concepts. Signal processing is based on lots of mathematical concepts, right? Based on lots of mathematical concepts and mathematical like statistics, concepts, right? And it is basically like going towards like statistics, applied statistics, right? Applied statistics, where we apply the statistics on some kind of a scenario. We consider a certain scenario. Depending on the characteristics of that scenario, we use the statistics. So for applied statistics, so we are focusing on using like applied statistics on situations, and we use this applied statistics knowledge as a tool to do the signal processing. So in signal processing, we will be talking about statistics in basically like statistics and mathematics, right? So basically mathematics, statistics will be discussed, and we will be focusing on those. So we will be having like things like mean, mean, average of a certain function, right? We'll be talking about the mean. We'll be talking about the variance, right? we'll be talking about the probability. We'll be talking about the probability. We'll be talking about the probability density function. Probability density function, right? Then we have cumulative density function. Cumulative density function, right? So we have different statistics like that. So yeah, we call this cumulative probability distribution function. Okay, cumulative distribution function. So we will get into those later. I'm just telling. Then we will, talk about other statistics as well. So let's, discuss about that. So anyway, what I wanted to summarize is that like we are using a lot of, concepts that are used in applied statistics in this signal processing domain. So we also have like I would like to mention some like likelihood. We have some other concepts such as likelihood estimation, right? That means one of the estimation techniques, likelihood estimation, linear regression. So those things, linear regression, right? Linear regression. So these are also related to statistics. So uh, so those are the things we have to, we will be discussing mainly. So as I said before, we have to, evaluate random signals. We have to evaluate random signals in order for us to uh, in order for us to uh, get the information from those random signals. We have to work with these random signals. So in order to mathematically model the random signals, we are using concepts such as random variables, right? So we are using this random variables concept where we are defining a certain variable to define the randomness of the signal. We are using like variables such as x, y. Likewise, we are using some variables to define the random signal or the random process that we are considering. Okay, so we will get into that later. Anyway, now these are the things that we will be using. These are the kind of terms that we will be using, definitions we will be using to mathematically model the random signals. Then we will be using random processes, right? Random variables, random processes. Likewise, we will be discussing about random signals, right? So basically random variables, random processes, and inside these random variables, random processes, there are other like mathematical definitions. We will get to them once we discuss these topics separately, right? So first of all, we will discuss about the random variables, right? So we need to first discuss about these random variables, and then we need to discuss about this random process, which we will discuss after we have completed the random variables, right? So have you learned about random variables during in a previous lesson or in your bachelor's or somewhere else. Have you learned about the random variables? Yes. So yeah. So most of the time, if you have followed courses related to probability, random signals, and then estimation, probability, random signals, uh, signals and systems, signals and systems, um, uh, and other, digital signal processing. You would have learned about these signals. Also, in other modules related to maybe control, control and automation, you may have learned about uh, these definitions. Anyway, I'm just asking, it's not necessary, but like you these are concepts that are widely discussed in the world uh, in modules, in lectures. So this is widely available concepts. So I think we will take a small break of 5 minutes, and then we will start about random variables. Right. So yeah. So we will first define the random variables, and then we will discuss about the random processes. Right? So we will first discuss about these random variables, then we will discuss about the random processes. Right? Random processes can be modeled using random variables. So variables, right? Random variables. Random variables, right, are used to um, analyze random signals. They are used to analyze random signals. To analyze random signals. So, and mathematically model the random signals. Mathematically model the random signals. They are used to mathematically model the random signals. So for example, like let's say any kind of random signal, such as, for example, ECG, uh, they can be used. The ECG can be modeled using random variables, right? So random variables are used to model the random signals, such as, for example, ECG, right? Music signals, so on and so on. So how can we define the random variable? What are the parameters of a random variable? So, right? So what is a random variable? What is a random variable? Right? So there are four elements. There are mainly three, no, four elements. There are four elements that we can use, to define a random variable. Four elements we can use to define. There are four elements. Um, used to that can be used to define a random variable. I will call the random variable as capital RV. So the first thing is we need to have a certain experiment, right? We need to first we need to have a certain experiment that can create random outputs. Physical experiment that creates that has random outputs, right? That has random outcomes, and the outcomes should be the outcomes should be modeled. Outcomes should be modeled as real values. Should be modeled as real values. As real values, right? The outcomes of that experiment uh, should be we should be able to model them as real values, right? So the real values could be integer value or it could be a floating value, continuous, I mean floating value. Then there should be some kind of a sample space where we should be able to find all the possible outcomes. There should be a sample space which has the collection of all the possible outcomes. All the possible outcomes. So we need to know the all possible outcomes from that experiment that we conduct. And then we need to know what is the probability. We need to know the probability associated. We need to know the probability associated with each outcome. Right? We need to know the probability associated with each outcome. Right? We need to know the probability associated with each of the outcomes. Once we know all this, we can define a random variable. Right? We need to know all this to define a random variable. Right? So let's take an example. Right? Let's take a very simple example. I'm going to erase this. Right? So the smallest example I think that we can take. So we will take the experiment as the experiment of rolling a dice with fair sides. Rolling a dice with fair sides. With fair sides. Okay, so rolling a dice with fair sides. So once we are rolling a dice, since it is like very fair, it has fair sides, then we don't know exactly what is the output going to be. Right? It is a very unpredictable event. Right? However, we know that like there are 6 sides to it, and the probability of getting one side is going to be the total number of times that one side can be taken over the total, I mean, possibility of taking all the other sides. So anyway, like we can define the outcomes of this, right? We can define the outcomes, possible outcomes of this experiment using real values, right? We can define the outcomes of this experiment using real values. So one outcome, let's say the outcomes I will denote as this tau. first outcome I will denote as 1, right? Getting the side 1 or the side with the 1 in this dice, I will denote as 1. Then tau 2 is getting the number 2 is, I will define that outcome as 2, and likewise I will define for all the outcomes a certain real value, right? So sorry. So this is getting the getting 1 from the dice. This is getting 5 from the dice. So getting 5 I denote as 5. So I can therefore denote all the outcomes as a real value. Then thirdly, I need to understand how I can define the sample space. So the sample space for this experiment will be the collection of all the outcomes, and the collection of all the outcomes as a real number. Right? This is the sample space is tau 1, tau 2, tau 3, tau 4, tau 5, and tau 6. So the sample space I can write as 1, 2, 3, 4, 5, 6. Right? And then finally, I should be able to give the probability that is associated with each of the outcome. Right? So I need to be able to tell what is the probability of getting tau equals tau 1. Right? So the probability of getting 1 out of all the other outcomes is, I think we can take it as 1 over 6, right? Because getting the outcome of 1 is um, getting an outcome of 1 is 1 out of 6, because the getting each of these outcomes is equally likely. We can get each of these outcomes in an with equal probability. So the summation of the probability of getting each of these outcomes should equal to 1. So because of that, getting the outcome 1 uh, should be equal to the probability of 1 over 6. Likewise, we can define that for all the other tau values also, the value of the probability is going to be 1 over 6. So that is, I think, a very simple example, and by that I think we can understand how we can form a random variable. Right? Random variable can be formed by defining a kind of random experiment and defining the outputs into a real value, and then making sure that we know all the outcomes of that experiment, and defining the sample space with that information. And then by that information, then we need to derive the probability of each outcome happening. So that is basically regarding probability and random variables. I think we are not going to talk about probability much. Therefore, I think we will proceed with that uh, stage to the stage where we are uh, analyzing the random signals, right? So we will go bit further than probability theory in this module, and uh, we use that to analyze the random signals. So I will erase this slide. So random variables, we learned about the different elements, different parameters, or I mean different properties of the random variables. So there are many random variables that are defined in the world, and we can categorize the random variables into basically 3 types. We can define them as discrete random variables, continuous random variables and then mixed random variables. Right. So let's talk about the discrete random variables. So what are discrete random variables? Right. So discrete random variables means the random variables which has countable outcomes, right? Countable outcomes. So, right? So if there's a certain, like an experiment, random experiment that has countable outcomes that we can count, like 1, 2, 3, 4, 5. Likewise, if we can count the number of outcomes, then that random uh, that random that random variable that is used to define that experiment is known as a discrete random variable. Uh, right? So if we go to the continuous random variable, it is having uncountable outcomes. Uncountable outcomes. What do we mean by that? Right? Uncountable outcomes. That means it has like infinity amount of outcomes. The reason being the outcomes are from minus infinity to like plus infinity, right? So the outcomes are all there between minus infinity and plus infinity, right? So the values that are in between this minus infinity and plus infinity is uh, can occur for this specific experiment. Any value between these kind of, I mean, ranges can happen. So I mean, let's say it is not exactly minus infinity plus infinity. Let's say -1 and +1, right? Even if we take -1 and +1, there are infinite number of outcomes that can that can happen between -1 and +1 if we consider both, you know, like floating points. If we consider the floating points, right? If we consider -1.00, likewise we can go up to infinity, right? So likewise, like we can define uncountable outcomes between the region we select. So if there's an experiment that has uncountable outcomes, just like that, then we say that that random variable that defines that experiment is a continuous random variable. And there could be other random variables which have both discrete and continuous random variables. Right? Discrete and random variable, sorry, continuous random variables. Right? There could be some random variables with both discrete and random variables uh, included in this random variable definition. So the mixed random variable is defined for a physical experiment that can have both countable outcomes and uncountable outcomes. I think I'm not having space. So that is basically regarding the definition of random variables. I mean, how we can like categorize them into different random variable types, right? So this is just the beginning. Okay, so we are going to go through discrete random variables, continuous random variables, mainly, and then we are going to discuss about them. So mixed random variables is a mixture or a combination of these two. So we are going to be focusing on discrete random variables and continuous random variables mainly, and that knowledge is sufficient for us to analyze the mixed random variables as well. So we will discuss about the discrete random variables and the continuous random variables. right? So I think I will erase this part. So the discrete random variables I will discuss, and also I will discuss about the continuous random variables. Right, so we will discuss in like comparison. Right, so when we talk about the discrete random variables, the random variables are described. The random variables are described using the probability mass function, right? The probability mass function. So if you have learned, I think you have heard about, I mean, if you have learned probability, must have heard about the probability mass function. And this probability mass function, let's denote it as PM, right? PM. Let's denote like this. I will explain about this term. So let's denote the probability mass function as PMX, where X is the value of the random variable, right? So X is the value of the random variable. So the probability mass function is defined specifically for the discrete random variables, right? So in contrast, for the continuous random variables, we define the continuous random variables. So we describe the continuous random variables using probability density function, right? Probability density function. Uh, we describe the random variable using probability density function, right? And probability density function we denote using the function. We will denote using simple F, capital X, and then inside we have simple X. So, right, capital X and then simple X. So this capital X is used to denote the name of the variable, name of the variable, name of the random variable, and this simple X is used to denote the value of the random variable, the value of the random variable. So the name of the random variable will remain fixed. The value of the random variable will vary. We will discuss about this in a like later instance. In general, in general, we notify this probability density function using this fx inside bracket simple x. So that is how we define the probability density function. And so in the discrete domain, we have probability mass function, right? So they are used to like define the probability of the random variable occurring, right? So these mass function and this probability density function, they're used to like define how the probability of each outcome is, right? So they are used to define the probability of each outcome of each outcome of the random variable, right? There are different outcomes that the random variable can take. So so the the probability of the each outcome of the random variable uh, we call as we use the this probability mass function and the probability density function to define the probability values. I think you must have learned about probability density function most of the time. Probability mass function is just the same. The difference is that for that function we are considering discrete random variables, and therefore the value of the probability is defined for each discrete random variable outcome. So like for example, if I draw something, the probability mass function looks like uh, a function or looks like a plot where we define the values of the probability of each of the outcomes. Let's say this is one. Let's say the outcomes of the physical experiment is 1, 2, 3, 4, 5. Then the random variable is, let's say it is x, right? The value of the random variable is given by x. The value of the random variable is given by x, simple x. And the random variable is discrete. So the random variable is discrete. It is not continuous. The random variable is not continuous. It is discrete. So for each of these discrete values, we have a probability of that value occurring, right? So we have certain probability. Let's say it is 1 over 4. Let's say it is 1 over 2. Likewise, we have some probability uh, associated with each of the outcomes. We can define a certain probability for each of these outcomes to occur, right? So that probability is given using this probability mass function distribution, right? So we we will denote it as PMX here. So the probability mass function looks like this. It looks like a discrete plot that is defined for discrete values of random variables. I hope it is clear. Then we have the other type where we have the random variable x, and in here the random variable x is continuous. So that means like if we have two values in the graph, let's say we have two values like 1 and 5, let's say, then all these intermediate values have a certain probability of occurring. So we define the probability of occurring as a uh, like a some kind of a probability density function. So the probability density function can take any shape. So I will take this shape for the moment. It is a normal distribution shape. So the probability that the uh, that the this value, which is 1, for example, can occur, can be given from this probability density function graph, right? And we will discuss about this probability density function as well, further as well. So for if I take, for example, if I take the value of 1, right, 1, which is the random variable, right? If I take the value of 1 using this graph, if I go to this value of the probability, right? So this function I will write as like fx and simple x, right? So this is a continuous function. So if I find the probability here, it's actually it is equal to 0, right? The probability of getting 1 is actually 0. Probability of getting 5 is actually 0. The reason is like this is a continuous random variable. This is a continuous function. And because of that, in order to find the probability, we need to find the probability of getting a value which is within a certain range, right? So if if I'm going to explain it further, we we do not have a value for probability for a certain one value, but we have value for the probability over a certain gap or a certain uh, distance. or a certain range in the random value. So the probability density function is defined, therefore, as I mean, probability density function is defined to define the probability of a continuous variable. And then from this function, in order for us to find the probability of a certain variable occurring, then we need to find the area under the curve over a certain range, right? So if I want to find, let's say, the value of probability around this one point, we need to take the area under that point in this curve. So that we can define using this expression. So we can take the value of the function over the dx that we consider, and then I can take the basically I can take the area that the area around that x point, right? So I don't need to integrate over the small distance, because this is a dx distance. So right, so if we are considering a dx distance, the height of the uh, height of the probability, or the value of the probability at 1 and 1 plus dx is almost the same, right? So if I want to find the area under here, then I need to just take the height, which is fx x, or in here the x value is 1, right? So fx inside brackets 1 into dx, that is the probability of getting 1, or 1 plus value between 1 and 1 plus dx, right? So it's actually written like this. So getting a value between 1 or 1 plus dx is defined by fx x, where x is equal to 1 into dx. This will give the probability of getting 1 in this probability density function. So in general, we define the probability of getting any value using the expression that I will write next. So you just need to substitute this 1 with the simple x. So these are, I think, some mathematical definitions. So if you have some problems, you can let me know if you cannot understand. So normally these are predefined standard functions that are defined in statistics, probability, random signals, areas. So you can refer them also through the reference books. So I will again write the probability of getting the value x, simple x, when the uh, random variable is defined, when I want to find the probability of getting x, then I have to compute this probability where the random variable is spanning over a small distance of dx, and then I can define that value. I can define that value as fx x into dx. So this is how probability density function is defined in general, and um, it is used widely to define the probability of continuous random variables, right? I will write that again in here, I think. So this is the definition of continuous random variables. So this probability, this definition is used to compute the probability of the random variable getting a value of x, right? So random value, uh, when the random value is equal to x, then the probability of getting that value x is given by this expression. So you can also further, try to prefer probability density functions So those functions are, I think, like baseline in understanding this module. So I think you can further, I mean, you can search about it. If you have any questions, you can ask from me. Uh, so we talked about the probability mass function, and we talked about the probability density function. So another property that are associated with these functions is that the area under these functions is equal to 1. So basically, it is defined by two expressions. I will write those as well to complete this discussion about these random variables, right? So basically, the area under the curve is going to be equal 1 for both of these scenarios. So PM x, the area under the curve, like the entire area under the curve, we can define by taking the minimum value of the random variable up to the maximum value of the random variable, and we can equal it to 1. And then we can take the continuous random variable, and in there we have to take the integration because we have continuous values for the random variables, and therefore we need to consider the integration in order to take into account all the in between values of the continuous variables. So in here we have x min, and up to x max we have the values of the random variable. So in here we have the continuous, I mean probability density function of the continuous variable, and then we have the dx, which is used to integrate over small distances in the probability function. And this total area under the curve is computed using this integration, and it should be equal to 1. So that those are the basic descriptions regarding those two uh, I mean two distribution functions, probability functions. And then I also want to mention that we uh, we need to know definitions related to those probability functions, right? So as I mentioned before, we are going to be working with statistics, a lot of statistics in this in this signal processing domain. So statistics related to probability mass function and statistics related to probability density function we need to study, right? So the statistics related to probability mass function and statistics related to probability density function will be basically like finding the expectation value of the random variable, how to find the expectation value of the random variable, right? So expectation, or the expectation of the random variable. So expectation is the average value, right? Average value of the random variable, right? So basically expectation value of the random variable we need to know, right, in order for us to analyze the random variable. So we need to know what is the average value that the random variable can take. So if we want to find that under discrete random variables, we need to get the average value, and that average value you can compute by considering uh, the mean value of the distribution. So we need to compute the mean value of the distribution. It's given by mu, and that value we need to consider, and we need to take the average of all the uh, all the values of the probabilities under the random variables. So apart from that, like for another parameter that we need to know is the variance. So the variance is uh, defined for the probability density function as well, and it is defined with respect to this mu value. So we will discuss about this, expectation operations and the variance operation for each of these two random variables. So we will discuss about the mean value, and then we will talk about the variance value. So the variance value is defined as uh, x minus mu's square value, or the expectation of x minus mu squared value. So this is defined as the variance of the distribution, and this is defined as the sigma squared. So uh, if I am going to elaborate further, so we can also define the standard distribution function, the standard deviation using the variance, right? We have to take the square root of the sigma squared to find the standard deviation. So for each uh, distribution function, we need to define the mean and the variance to understand its behavior. So these are the main two parameters that define a density function or a mass function. Right. So I will again go back to the definition of mean. Mathematically, I will define the definition of mean. So we can define the mean of a mass function by taking the product between the value of each random variable with its probability and taking the sum from the minimum random variable up to the maximum random variable that is possible. Right, so this is the definition to find the mean average or the mean value of the random variable, right? So for a discrete random variable, this is the equation that you need to follow. This is the equation that you need to follow to find the mean value, right? So in here we are taking the product between the random variable and its own probability value, right? For each x value, we are multiplying it with its probability value. So after doing that for each of the x values, you are going to take the sum between all that, and that sum will equal to the mu value, right? So that is how it is calculated mathematically. Okay, so this is a mathematical function that you can use to find the mu. And then we have for the continuous random variable also, the x value that is spanning, or the x value that is varying from the x mean value up to the x max value, and the integration should happen from x into fxx into dx. So by taking the product between the random variable and the probability value of that random variable and integrating it from the x mean up to the x max value, we can find the mean value of that distribution function, right? So that is basically regarding the mean value. So when we take let's consider like a probability density function that we can draw, right? I will take a general uh, probability density function, and in here, if I have to indicate the mu, I will indicate that the mu is in the center of that distribution function, right? So the distribution function, if it is uh, going in this manner, then we can define the mu value as the center location of the distribution, and in here we will have the mu value. And then if I then describe the variance will be defined using this width around this mu value. So the variance will be defined using this width, and it's not exactly equal to the width, but this width will be affected by the sigma or the variance. So the variance will affect the width around the mu, and it is defining the width of the distribution function and the shape of the distribution function. So basically, those are the two parameters that define a distribution in this probability distribution functions. Then we have for mass functions also the same thing. In here, actually, probability mass functions is a discrete value, and the discrete probability values are defined for each of the random variable values, and then we can take the mean value out of these uh, out of these uh, out of these values, and then we can define where the mean value is. So anyway, we can define like a curve for the probability mass function, I mean in order, and then we need to define a certain value for the mu. So the mu value can occur in somewhere in the real axis of the variable. So uh, so basically the mean value will be uh, defined using these equations. You can find the mean values using these equations and define the mean value for those functions. So those are the things related to the mean of the functions, and then I also want to describe about the variance. So I think you erase this section. So the variance is the other parameter that will define the two variables. So we have the discrete random variable and the continuous random variable. The discrete random variables variance value actually for both the discrete and continuous random variables, we can define the same variance equation. So that will be equal to Ex minus mu squared. So this is used to define the variance of the function, variance of the probability density function. So as I mentioned earlier, the variance is defined using this, variance is used to define the width of the probability function. So if I have the probability function like this, the variance is defining the width of the curve that we are considering. So anyway, like this is defined, the variance is defined using this expression where we take the expectation operation of x minus mu squared, right? In here, the mu is the mean or the expectation of x, right? So mean we discussed earlier, or the mean mu we discussed earlier. So same mu is considered here. So we need to take the difference between the random variable and the mean, and then we need to consider the square of that, and then we need to consider the expectation value of that term to find the variance of that distribution. And it is defined by these expressions, ex squared minus ex squared. So what I'm saying is basically this is equal to ex squared minus mu squared. This expression is mu, right? This is ex is mu, right? Ex is mu. So we can plug it in here, and then we can take the difference between ex squared minus mu squared. Once we take the difference, that is equal to the variance. So variance is related to mu uh, directly, and then the variance is also varying with the mu. So as I said before, you can find the standard deviation function, standard deviation value. I will, yeah, standard deviation. You can find that by taking the uh, square root of the variance. So the square root of the variance you can find by taking the square root of this expression, and then you can find the standard deviation value, OSTD I have mentioned here. So standard deviation function is uh, is also used to define a probability density function. So those are the statistics related to the probability density function, and those come useful for us when we are trying to study the signals and the random signals uh, that come into play when we deal with signals that come with the sensors and other devices. So whatever the devices that give us certain signal, they will have a certain probability distribution function. That means like that we can define a probability density function to each of the random signals, right? Random signals can be defined using the probability density functions, right? Then using the probability density functions, we can define uh, like what is the uh, what is the what is the random variable, or what is the parameter that what is the value of the parameter that occurs frequently, for example, right? So what I mean is like if, for example, if we consider an audio signal that we receive can have different amplitudes in it, right? An audio signal can have different amplitudes. So those amplitudes, if we plot the probability density function of those amplitudes, right? If I take the amplitude as the random variable, and if I if I plot the probability of each amplitude occurring uh, in, uh, using the experiment, then I can find what is the amplitude that is occurring all the time or most of the time. So that average value, I can say the mean of that distribution, right? So I can say, okay, this specific mean value of amplitude is happening frequently in this audio signal. Likewise, I can say, apart from that, I can say, okay, what is the variance of this amplitude variation? How does this amplitude vary with the time and around the mean, around the average value? So so by plotting the probability density function of a certain random signal, I can understand its mean and its variance, right? So using those parameters, I can do some predictions regarding the signal. So like that is the, I think, basic idea regarding the random signals and probability density functions. So right, so I think these are like the baseline knowledge that you must have learned in previous modules regarding probability and distribution functions. However, like I have covered like the basic statistics that you need in order to mathematically like model the probability density function of a certain random signal, right? And that is basically what I wanted to mention basically. And uh, we will uh, we will discuss about um, we will discuss about useful random variables that we use uh, in maybe in a little while. So I mean, uh, there are like some useful random variables that we use to define signals that we use every day. For example, like we use Gaussian random variable frequently. We use Gaussian random variables very frequently in our processing. Uh, I mean, in signal processing domain to like model like signals such as noise signals, then measurement errors of sensors. Like measurement errors of sensors, we define using Gaussian random variable, and then student grades, student grades, and then biological signals, biological signals, right? So we use Gaussian random variables to model different signals such as noise signals that we observe very frequently in for example in communication, uh, where we have to face the noise addition into our communicated signal. So when we are receiving signals, for example, through our communication links, we receive noise as well. So we need to understand what is the distribution of this noise signal, what is the average of that noise signal, and what are the other parameters that define this noise signal. And that is why we need the probability distribution functions, right? And then measurement errors in the sensors. What is the like what is the distribution of the measurement errors? And that is the place where we require the probability density functions. And then student grades and biological signals. Likewise, we need the probability density functions to define the these signals, and we use that to define the probability of the signals and under the certain random variable we are considering. So I will discuss about those maybe in a later instance. We will do some like Matlab simulations in a little while. I thought of discussing about some Matlab simulations that we can use. So we will take a small break of 5 minutes, and then we will I think resume. If you have any questions, you can let me know. So there's a question, so we can have the slides. Yeah, so actually I do not have any slides, so I'm having only my written note that I prepare, I think, before the lecture. However, I will provide you some notes regarding the sections that I'm covering before the class, and I will upload into the LMS before the class. So do you have access to the LMS? Do you have the SLTC email?
Yes.
Okay, yeah, sure. Then I think you can access the LMS, and then I will discuss about that in I think at about 11:30 or something after we do the MATLAB simulation, and then we will discuss about any issues that we have regarding the modules and regarding the program if you have. So I I will share with you one link that possibly you can use to one thing is you need MATLAB installed in your computer to do these simulations. I don't know whether you have the MATLAB installed in you. I know I have given MATLAB before in a workshop, but I don't know whether you have MATLAB versions of latest versions. Therefore, I think I will share with you one link. Hopefully you will be able to download from that, and I will put in this chat. So all right, maybe you can keep it saved somewhere, this link, and you can install the MATLAB, the latest version. So I will share my MATLAB screen. So in this signal processing module, I'm going to use uh, uh, a certain app. So we are going to use the app. I hope you can see. I'm going to use apps. I'm going to go to the signal analyzer app, and then I'm going to use that app to analyze or look at the signal in time domain and frequency domain basically. So if I want to go through the command window, I can type signal analyzer and I can go to that app directly. I think I already have it open, so therefore it doesn't open again. Either in that method, or you can go to the in the top menu, you can go to apps. There are certain apps, several apps that you can see. So in there you have signal analyzer app, right? Signal analyzer app. So this app you can select. So in this example, this is an example that is available in the MathWorks, MathWorks website as well. So I'm going to just follow these steps and do maybe some demonstration and show you how we can use the signal analyzer app. So in this section, they have provided us a song, a song, uh, and they have provided us the variable or the the data uh, of that song. They have provided us the data, and they have given that data a certain variable. So it is denoted using tune. So uh, so once I run this code, I can save the information of the song, of that certain song. There's a certain song that is defined by this code, and that song can be recorded by its amplitude, right? So like audio signal, it has certain amplitude at each time instance. So that amplitude value will be saved into this tune parameter, and I will have that tune parameter saved in the workspace. I will first run this part. I will go to editor and I will run this. Then once I run it, I will be able to see in the workspace on this space, on this place, I will be able to see like a variable or a parameter tune, called tune, right? And then I can use this parameter in my signal analyzer app. What I need to do is I can just use drag and drop, and I can put in here, or else I can also, I think it automatically comes up in here once I run the command in the normal MATLAB command window. Automatically the signal analyzer app takes that parameter into its web workspace, right? So you can also check this. If not, you can take that this tune parameter into you can drag and drop into the analyzer as well, or else normally this tune should appear here as a variable. So if I want to analyze or study that, I will consider the tune, I mean that variable in the in the in this section, in the top section. I will drag it from below to the top, and then uh, I will I will have the tune song in here. So I will put a tick, and this is the song that I have. So this song is plotted with respect to the time. So I think you can't see the screen, right? So I will again share it. Sorry. This is the analyzer app, and in here you have tune parameter, and I have considered the tune. I have dragged it to the top, and then I have selected the tune, and then by selecting I can see the signal, the plot of the signal. The plot of the signal is a variation of the amplitude with respect to time, right? So this is a signal that I I have, but what I want to do is I want to like the uh, see the effects if I try to filter this signal uh, under different frequency bands, right? And I can do any kind of analysis. I'm just trying to filter this, but you can do like some you can observe the frequency components of this signal, and you can calculate the amplitudes of the signal. Likewise, uh, you can consider. So if I want to see the frequency components, I have to press the spectrum part, and then I have to I will remove this from this display. What I want is just one plot, so I'm going to just go to one plot, and then I think I'm able to obtain this. Anyway, it's not like you can go through the tool if you want, if you have free time. So do you have any questions regarding the simulation? You have, you can let me know. So this is like how you can observe the spectrum or the spectral components of the signal, right? The signal which was in the time domain. So we have now got the two plots of the signal. In one we got in time domain, second one we have in the frequency domain. So then if I want to do further processing, I can apply some filters on this signal. So if I want to find the filtered signal, I can do that by using filters that are available in the tool. So I can go to analyzer, and in there we have different filter options that are available. Like there's low pass filter, high pass filter, band pass filter, band stop filters, resample, detrend, envelope. Likewise, there are several functions. So what I will do is I will remove this plot for the moment. I will create duplicates of this, and I will create 3 duplicates of this. So first one I will rename so high. First one I will replace as high, and second one I will name as medium, third one as low. So what I want to do with the first one is that I want to filter the high frequencies and plot those in under this high plot, right? Since I got the duplicates of the original signal, the entire signal components will be there appearing under this plot currently. And now I want to apply the filter. So I just directly go to the analyzer tab. I go to high pass. There are high pass filters. So high pass, and then I enter a certain frequency above which I want to filter the frequency. So I want to filter frequencies above 450 hertz. So I put 450, and then I can define the steepness of the filter. So steepness of filter means steepness of filter means the filter uh, around the cutoff frequency, right? So you can make it a high value to make the steepness high around the cutoff frequency. That means like around the cutoff frequency, the the filter is very strict. The filter is not smooth. Filter is not curved. It is fully like vertical. I hope it is clear to you. If you are not understanding, you can let me know. So normally filter functions are like steep, right? Steep functions, and they are having certain steep around the cutoff frequency. Anyway, I set it to 0.95, and that is all I'm going to do. And then I'm going to run the high pass button in here. Then it will apply the high pass filter on this signal. And as you can see, the low frequencies that were there in the signal, right? Can you see the filters outputs? I hope it is clear, right? So the filter output is like this. So the low frequencies, then like 450 hertz, have been cut off, and then the other frequencies have been retained. They are remaining. Okay, so the other frequencies above 450 hertz are remaining, and they are shown. So this is the frequency plot, and related the time time domain plot is given in the top plot, and the amplitudes that are remaining after the filtering is given here. So after we apply the filter, there's a symbol that is occurring or shown in this this in this interface. So if you see this sign, you know that filtering operation has been done. So that is how you can make sure the filtering has been done on a certain signal. And then you have the sorry, I will keep it. I will keep it. Then I want to do filtering under the band pass region. So I will add another plot in here. The second plot, I'm going to draw the band pass field, and I'm going to add the spectrum, frequency spectrum, and I'm going to plot it now. And now I'm going to select this for this plot. I'm going to select the medium, and I'm going to apply the filter band pass. So band pass filter, sorry, band pass. So band pass filter, I'm defining between 230 hertz and 400, 400, can't, 450. So Those are the frequency values I'm defining as the passband, lower passband frequency, one thing, and the upper passband frequency, right? So in passband, sorry, yeah, band pass filters, we have the uh, lower passband frequency and the upper passband frequency. Those two values I define here as 230 Hertz and 450 Hertz. And then I have the steepness. I will increase it up to 0.95, which is actually quite a high value, but I'm doing it to make sure I cut the signal. I do the filtering exactly around that frequency. Then I apply the band pass filter. So I hope you can see the band pass filter has frequencies from 230 hertz up to 450 hertz. The respective audio signal is in the top plot in blue color. And then third filter I will add as low pass filter, and that low pass filter plot, yeah, low pass filter plot I will select. Then I will select low here, and then I will select spectrum on top, and then again I will select the low pass filter option, and then I will select the passband frequency as 230 hertz, and then I will give the steep value as 0.5, and select low pass, and then I can do the low pass filtering on that signal. So the frequency plot shows that after 230 frequency, the frequency components have degraded and attenuated, and only the frequency components during in this small, in the frequency range below 230 hertz is available. So as you can see, now we were able to apply filters on our signal that we had initially, and we have applied low pass filter, band pass filter, and the high pass filter. So now we will also look at the effect of that filtering on our output, right? So once we do the filtering, what is the output that is occurring? So I will let you hear that. I hope you will be able to hear. So I will run this. So I get a plot. I get a plot of all the. One thing is I get a plot first, right? Like this. I will explain. Also, you will hear some sounds. I don't know whether you will hear. I will try to run this again. You are not hearing, I think. I think I also need to define the frequency. So also, I think, sorry, I forgot. I need to go back. I need to go back here. I need to select. I need to export the data into the Matlab window. Otherwise, the data won't go there. So I will select all this, and I will export this data as export mat file, and I will export it as music. I will export. Yes. So there's a music file that has appeared. Therefore, now it has data, hopefully. And now I will be able to hear some music. Don't know whether. So there are some music in here. So I think one thing is uh, high, one thing is low, one thing is medium. So anyway, I will first go through this plot. This plot is the combination of all the filtered signals. So the filtered signals in the frequency domain. So the blue color plot shows the low pass filters frequency domain plot. And so you can see only the low pass filter frequencies are available in this plot. The amplitudes of all the other components are almost like low, very low, and it is in the range of minus 140 dB, right? So in general, I mean, if we take the value of the signal, if it is below like maybe minus 50, you can't hear that audio signal much. So if it goes below maybe minus 50, minus 60, then you can't hear these frequencies. It is not audible for the human ears. So only the frequency, the signals which are in this frequency range, you will hear under this blue sound. Once you talk about the band pass one will have signal amplitudes only in the region between 230 up to 450. And then therefore, the orange plot is like slowly increasing and then decreasing. And then third plot, which is in yellow, which is having amplitude like below 60 dBm, below 60 dBm, will have amplitude, considerable amplitude after 450 Hertz. And it will have a function like this. So this is the plot of the filtered signals. Now I want to obtain the sound signal. I don't know whether you can. I think you can hear. Oh, sorry. I will now stop now. Right. So I will comment these two. So basically, sound. The first command gives the sound value of the low pass filtered signal. Right. So only the low pass or the low frequency components of the song will be heard, right? So initially we had a song. So so first of all, I think play that one. So right, I need to first initially play the initial song. So this one. So that is the initial song. And then I have low pass filtered it. I have only kept the low pass frequencies, and I have removed the high frequencies. So listen to this and see whether like you can hear high frequency components, because I have removed those. I have only retained the low frequency components in this sound. I will replay it. Okay. The second one I will play. then I hope you can understand that it is a band pass filtered signal. It has the medium frequency components. So I think in that third signal, we had high frequency components, right? So I hope it was kind of clear. If you have any questions, I can verify. Apart from that, I have these codes I will share with you, and you can also do the same, or else actually this is a example from the MathWorks. You can follow this example exactly. So what you need to do is you need to run this command in the MathWorks. I will put that in the chat. You need to run this command in the MATLAB window. Then you can see the example, and you can see what are the steps that you need to follow in order to obtain the results, right? So then you can also do the same thing for your own audio signal, right? You can do the same thing for your own audio signals. So that also, I think I have a sample like scenario that I can show you. I will, I think, maybe show you in the maybe next class. So for now, I think I will try to wrap up today's class. So I wanted to discuss with you, like, so I think you have some access to the LMS. So in the LMS, we will upload all the information. If you don't know how to access LMS or have some issues accessing it, you can email it to me, or you can, yeah, you can just email it to me to my email address. I think you know my email address. You can email it to me. Apart from that, I also want to mention to you, I have created a space for you to contact me, and I will share that link now, right? I have created a space in the Google space, and I will share that link in this chat, and also I will share that link in the LMS announcement section. You can please, I want you to join to this chat, and you can ask any questions you have regarding the module through that chat if you have any questions. Apart from that, I will upload today's video into the LMS. You can take down if you want a note. I think I recommend you taking down a note before the exam. Apart from that, I think I will explain to you regarding the plan of this module in the next class as well. So there will be, anyway, like I will explain now, like briefly, like that there's going to be a mid exam, like a small mid exam, and then also an end exam. Apart from that, I will give some, assignments for you to do using MATLAB, and applying the, concepts that we discuss in the class in MATLAB environment. So because of that, I want you to download the latest MATLAB versions that you can find, and use that to do the assignments. All right. Do you have any questions to ask about the module?
Madam, is there a reference book for this module?
I will provide you that reference book. I think there are multiple reference books. So I will provide those books in the LMS. In the resource category, I will create a resource section, and then in there I will include the books and any other resource materials that you can refer to study this subject. So as I said before, this subject is a little bit like towards statistics area. So I have to give you the mathematical expressions therefore, and I have to try to align it with the random signals that that we are going to analyze. So aligning the mathematical models with random signals is something that I will be discussing. And if you have any questions, you can ask. Another important announcement that I wanted to mention is that today you won't have the embedded systems module. So in that time slot, you won't have the lecture. Afterwards, you will have the digital communications lecture at 4. So if possible, please join at 4 to the digital communications lecture. After that, in the next week, you will have on Thursdays, you will have the leadership skills module. And on Fridays, you will have the Matlab module. On Saturday, we will continue as usual with this module and the rest of the modules. So that is regarding that course. Do you have any other questions?
Madam, is this MATLAB free version or is it paid version?
The link that I shared with you, I think it's a free one. It is available in the website in the internet. You can check. I think it is free.
Thank you.
Yeah, try to install the latest version that you can find. I think you can download the files from that link and then follow the instructions in the README file, and that would be fine. So, like if you can obtain the latest version, you can have a lot of functions in your MATLAB. Anyway, like even with the basic functions, I think you can follow these sections that I'm like explaining. However, I think sometimes some MATLAB versions do not have the signal analyzer app in it. So therefore, try to find one that has it. That is basically regarding this module. So I think, end today's lecture. And if you have any questions, you can stay. Otherwise, you can leave. I will put the recording to the LMS. Regarding assignments, labs, and other exams, I will also discuss in the next class as well. So thank you for joining today.